Hi guys, here's that long-awaited help for homework 13 and kind of the replacement lesson that we would have had on Wednesday if it weren't for that glorious awards night you guys are all going to. So here it goes. First thing is that we have to learn how to take the derivative of that e to the x function, that exponential function. Remember, that's continuous growth all over an infinite number of compounding periods. And so here's that e to the x function. It has an awesome derivative. I showed this in class as well. The derivative of e to the x is e to the x. Now, it's slightly more complicated than that. So what if it's not e to the x? It's actually e to the x dx that comes after it, which cancels to 1. If you think of it that way, we can actually see the next one a little easier. What if I have some e to the u? Let's say u is some function. U is a kind of a generic way of writing, hey, some crazy complicated function, let's just call it u. If I take the derivative of e to u, the derivative of that is e to the u, just rewrite it, then next to it you take the derivative of that exponent, that u thing, and just multiply it. Okay, so you always rewrite the function, the e function you're taking the derivative of, times the derivative of whatever the exponent is. So another way to write it is you call e to the u times u prime. Here's a quick example. Okay, so this is actually a chain rule. You're taking the derivative of e to the u and then the derivative of its inside, which is its exponent u. That's actually called the chain rule. Let's do an actual function instead of u. Let's call it x cubed plus 2x. That's our function. That's our inside of the e exponential function. The derivative, you start with rewriting it. That's the coolest thing about the derivative of e to something. You rewrite the e to the something. Then you multiply by the derivative of that exponent right next to it. So 3x squared plus 2, and that's it. Done. That's the derivative of e to any function. You rewrite it, e to any function, times the derivative of that exponential, that thing in the exponent. So in the, here's do one more quick one. 5x to the fourth plus x squared is in the exponent of e. The derivative, you rewrite it first, then the derivative of the exponent. Done. And I'm not going to worry too much about simplifying yet. There are ways that we usually factor out things when we're simplifying when e is present. But right now, keep it simple. Here's one from WebAssign. It'll be similar to the one you have. So I want to take the derivative of e to the 2x. You rewrite it, e to the 2x first. So I have that. Then you take the derivative of the 2 over x piece. Well, 2 over x, off to the side, I'm going to take the derivative of 2 over x. So you notice you would rewrite it as 2x to the negative 1. And then the derivative of that we all know is negative 2x to the negative 2. That's I put into the parentheses up above. So when I say take the derivative of e to the 2 over x, I rewrite it, e to the 2 over x, and then times the derivative of 2 over x, which you can do off to the side. Some people like to do that. They go off and do that derivative somewhere and then shove it into the parentheses next to the original function. Okay, here's another thing we need to keep track of. Remember the constant multiplier rule? Way back in the beginning we mentioned this. If you have a 3 times something, your function, you can just pull it out, ignore it, take the derivative, and put it back when you're done. So I'm going to ignore it for a minute. So let's say I don't have a 3. Okay, so I took off that 3, and I rewrite x, that square root of x, as x to the 1/2. Now that's, remember the 3 used to be there. I took it away. Okay, but I'll put it back, I promise. The next thing you do is, all right, when you take the derivative of e to the x to the 1/2, I rewrite it, e to the x to 1/2 times the derivative of x to the 1/2, which is 1/2 x to the negative 1/2. I'm done, except I have to put my 3 back, of course. So everything's good. I'm going to simplify a little bit, just for those of you who want to see, like, x to the negative 1/2 is 1 over the square root of x. So I rewrote that for you. Then what else can I do for you? So you see that simplified there. We can also multiply this out a little bit. The 1/2 times the 1 over the square root of x is just 2 times radical x in the denominator, and I went ahead and put e to the x to the 1/2 up top and called it square root of x again. Okay, so all of that simplifying is optional. All 3 of these that you see circled are equivalent and would work, and don't forget all 3 of them are missing the 3 that I need in there, so there's the 3 back in there, and you could write whichever one you want into the box for WebAssign. Next one is a product rule. Do you see the product rule in there? 6x cubed is our first, e to the negative x is our second. So I've set up the product rule for you. All we're going to do is fill in the blanks. So you know how you do that. Derivative of the first, there it is. Second unchanged. Derivative of the second, which would be the derivative of e to the negative x, which would be e to the negative x times the derivative of negative x, which is negative 1. and then rewrite the first 6x cubed. I'm not going to simplify in this case. You can just shove it all in there, and WebAssign would love it. If you want to simplify, let me point out a few things. You would factor out in the x squared or x cubed, the x terms, as much as you could. Well, I can divide a 6x squared out of both of those. I could also get out an e to the negative x. They both have an e to the negative x. Okay, what's left after dividing those things out of there, literally when you factor out, you divide them out, is 3 minus x. Okay, so factoring is from the days way back. It's helpful in contexts when I want to find when the derivative is equal to 0, for instance, where a relative maximum or relative minimum are occurring, the things we did before. It's good to factor if you're looking for a relative max or minimum where the derivative is equal to 0, because I can eyeball right now, I can see, I know that